Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll continue our discussion on Gaussian mixture models. Moving on to part 4, what we are going to look at is what would we do if we do not know how many clusters are there in the dataset ahead of time. So if we have infinite clusters situation, how do we deal with that? And there's two terminologies that we are going to use here. Components. So components could be clusters with or without data, and that's something would be difficult to understand. How could there be a cluster without data? But it will get clear as we walk through this. And clusters would be the clusters with data, or groups with data. Now, the way this is implemented in Scikit-learn is using the stick breaking process. There are other methods as well, but here, because Scikit-learn uses this method, we will just discuss this method. And here, what we have up here is first to draw the probability row for each of the classes. We can use Dirichlet distribution, where the parameters input would be each separate hyperparameter for each separate class K. And in the stick breaking process, which we'll talk in just a moment, we would be using beta distribution to draw the value for row 1, and then use the Dirichlet distribution to draw values on the remaining set for rows. So this does not have A1 in this particular input hyperparameters. So the idea is like this, and I'll try to explain it in a less confusing way if I can. I hope I am able to do that. Let's imagine a stick of length 1. So that would be a total probability mass that we have. Now what we are going to do is we'll break a part of the stick. So we'll have the probability mass coming off from the stick and a part of it that remains on the stick. So the very first part we broke off, let's say we broke off part V1. So the beta proportion then for that part V1, we would be getting from a beta distribution where the input parameters would be A1 and A2 plus A3 plus A4 as shown up here. So we are subtracting A1 and therefore we do not have A1 because, and we are using that here. So the total mass broken off is rho 1 is equal to V1 that we get from this beta distribution. Next, what we do is whatever is remaining, we break off another piece, V2, and again, in this case, the hyperparameters for beta now are A2 and A3 plus A4, and the total mass broken off then is 1 minus V1, and so on for V3, and finally we are left with V4, and this is the notation for the total mass broken off uh, at the fourth step for row 4. Now, if we have infinite clusters, it's the same process that we would go through as before. So here we had these parameters. The difference here is that we have A1 and B1 instead listed, and all the A's could be set to 1 and all the B's could be set to a value that is greater than 0. and then so that would be the way. So the analogy of breaking the stick would continue to be the same. So that's in essence the Dirichlet stick breaking process, where we are fixing one parameter. And again, as we saw in this case, here is the mathematical notation. So we have Vk that comes from beta distribution of 1 and alpha. We set all the a's to 1, and we are saying that all the b's would be a value of alpha that is greater than 0, and then we can get the values for row k, which would be product of the relation that's shown here. Now let's look at the Dirichlet process in action. So here, so this is the code in Jupyter Notebook. What I'm doing is initializing this data point x to 1, 1, and then within this for loop, uh, I'm setting the concentration parameter to 10, and within here, I'm creating a new data point, um, and will be iterating for 300 times, and using the Bayesian Gaussian mixture, with where we can input the concentration parameter, fit it on x, and then predict the value. And we are trying to predict the class, and what I'm trying to do is plot this class as it is predicted for each of these new data points. So what uh, what I want to show is, if you look at this particular plot here, we'll look at the animation shortly, but before we do that, what happens is, as the very first point when we begin the process, the very first iteration, all the clusters would be empty. So when a new data point comes in, it gets assigned to, let's say, cluster 1. So these are the cluster numbers. So cluster, there are 12 clusters right here. So cluster 1, then after that a second data point comes in. So that data point can now be either assigned to cluster 1 that already exists, or it could be assigned to a new cluster 2 that could be uh, in which there is no data point yet. Similarly, if a third data point comes in, now it could be assigned to either cluster 1, or it could be assigned to cluster 2, or it could be assigned to a new cluster 3, and so on. The process continues to repeat, and that's what I'm trying to show here. So let's run this. So here we first have, we can try to set the concentration parameter, let's say 0.0001, and run this. I'm going to run those libraries, and let's run this now. So this is how we can see, as the new data points are coming in, they are getting assigned. Right now we have just 3 clusters. One is labeled, one at 0, 1 and 2. So with the value of the input hyperparameters set to very low number, we see that most of the values are uh, put into the cluster 0, as we can see by this line. There are some data points going to clusters, other clusters. So we now have a total of 6 clusters that are created, and we still have 200 more data points to go. So this process would continue, and we may be able to see a few more data points and joining the cluster 1. So if you look at this Dirichlet process, if you read about it more, the general idea is that if there are clusters that already have data points in them, the chance that a new data point would get assigned to a data point that has data already has some data points is more than getting assigned to an empty cluster. So I'm going to stop this run right here, and we'll look at we'll update the values for the hyperparameter and run this again. Maybe set this to just 100. Okay, I've stopped this now, and let's go back up. I'm going to change this to 100 iterations, and let's change the concentration to 1 and see what we get. So why don't we do this? I'll keep this as 0.001 and copy this entire thing and then paste it down here. Maybe create more cells. And the idea is to then compare how different they are. So we'll put that as 1 and run this. So with 1, as we can see, the way these data points are getting assigned is little different than what we had with the value for 0.001. And here we can see that uh, still the cluster 0 has more data points, but then we just have 4 clusters so far. And we have more data points going into the newly formed cluster 1 and the cluster 2. And uh, here, as compared to beta distribution, we didn't expect that this would be a uniform distribution. And accordingly, we do still see higher number of data points assigned to the cluster 1. Next, let's uh, add another layer to this and run this with a concentration value for 10. So with 10, now what we are trying to do is we are moving towards equal assigning equal weight to the data points. But as we can see, they are still getting randomly assigned to all these clusters. We have 8 clusters so far, maybe 9 clusters. And so as we can see, in this case, maybe little less data points were assigned to cluster 0 as compared to the other clusters. So that's the 100. So okay, so that's with 10, and now let's try a very high value. So let's try maybe 10,000, and in this case, the values are they are they look different. As you can see, it is becoming very easy to create more clusters. So we have already reached 20 separate clusters or 35, and we can see the big difference that the tendency is to assign an incoming new data point to an empty cluster rather than assigning it to a cluster that already has some data points. So the cluster 0 has very few data points in this particular scenario where the value of hyperparameter is much higher. And we've already reached 40 plus clusters, and we can see this increasing trend as the Dirichlet process continues. And by the time we reached 100, we are close to maybe 45, 48 clusters. So that's this is wrong here. N components is not 0. So that's the whole idea behind the Dirichlet process. As you can see, with higher values of hyperparameters, this is how the data is generated. As we go on reducing the value of hyperparameters, as we can see down here, we start putting more and more emphasis on one of the clusters. Now let's get back into the PowerPoint slides, and here the question that we can ask is, why do we care about the Dirichlet process? And the reason is we do not need to specify the number of clusters ahead of time to be found in a dataset. So this could be useful in instances where we cannot visualize the data, and even if we are able to visualize, the structure of the data is such that we cannot identify any clusters visually in the dataset to set the value of k. So the Dirichlet process could help in those instances where it is able to find the optimal number of clusters. Now, what is variational inference and why are we using it? So as we looked earlier, in when we are trying to estimate the posterior based on the likelihood and prior, the denominator, which is the evidence, can become difficult to calculate even for the computers. And so mm, there is alternative way to uh, find the value for the posterior, and that's uh, where the variational inference comes in, the methods within the variational inference coming, and that's where the KL divergence is also used, as we discussed earlier, which is Kullback-leibler divergence, and it tells us how similar or how different the two distributions are. So lower the value, the similar those two distributions are, farther the value, the different they are, and that's used to gauge the iterations when we are trying to optimize. Now, random initialization is needed in these methods, and initialization can affect what the final results would be. So the general idea is to run initial maybe k-means to get a general idea on the cost associated with that type of initialization, uh, and then find the values for seeds that give the lowest cost, and then use that in the next steps. And then these could be of different types: random, distance based, or both, or those could be out of sample points. Now, how do we know if the number of clusters that we have found is good or bad, or is it optimal? So that could be to help kind of approximate that, we can use the BIC score. So the lower the score, the better it, so the better it is. And finally, we have the comparison between the two methods that are available in Scikit-learn: Gaussian mixture and the Bayesian Gaussian mixture. So the Bayesian Gaussian mixture uses the variational inference, the Dirichlet process that we discussed in the latter part of this series of videos, and the initial part where we talked more about the k-means is what the Gaussian mixture uses. So in Bayesian Gaussian mixture, points to note is that we can specify the weight concentration prior type, which is the Dirichlet process by default, and we can specify the values for the weight concentration, which is none by default, and we can set the value for tolerance. So in the stick breaking process, this would be used. And on the left hand side, we have again the n components, and then we have initial parameters can be found by k means, and then we have the initial weights and initial means. And again, this also has the initial parameters that can be found by k means. It's just not highlighted in orange. The code snippet is simple. We have the library Scikit-learn.mixture. We can import Gaussian mixture or Bayesian Gaussian mixture, and we can fit it to our train set. Of course, there won't be any y target that we need in this particular fit method, and then that can be used to predict based on the test set to find the cluster. That was it for this video. I hope in this video you got some intuition about what these methods are and how they are relevant to the Gaussian mixture models. In the next video, we'll look at the implementation in in Python using Scikit-learn. Please like, share, and subscribe. I hope to see you all in the next video. Thank you.